Hey again, welcome back to Venus. And we left off last time. I was talking about how we don't really do a lot with Venus in terms of sending probes, especially to the surface of Venus. The Russians did that back in the 70s, and that's it. Um, so I was trying to motivate the next future scientists of Venus to get inspired and maybe the next few decades graduate, go to college, get a good background in astronomy and physics, and or maybe engineering, and build a lander and go to Venus. But anyway, um, I digress. So what we were talking about in this part was where did these two continents? Let's just review real quick. Where did these two right here continents, Ishtar Terra and Aphrodite Terra, come from, or how do they form? So, that's a big mystery. It'd be nice to find more out about that. Venus has lots of evidence, though, for past volcanic activity. So when we do look at the surface, I'm going to go way back to the beginning here. You see lots of evidence here. I'm not going to go into extreme detail, but you'll see actual volcanoes, and you'll see large lava flows. On Mars, we tend to think that most of those are caused by water, although there's probably some lava flows that look like water flows. But on Venus, there's no sign of water. It's really hot. Liquid water cannot cannot be stable at this temperature, and so these are most likely all lava flows, large lava flows. So there must be a lot of volcanic activity, either in the past or currently, or both. Yeah, so those river-like lava flows that I just showed you there are called rills, and they can be thousands of kilometers long on Venus. It's impressive. There's also a lot of shield volcanoes, and if you remember in Mars, when I talked about um, the shield volcanoes in there, Hawaii on Earth is like a shield volcano. Basically, you have the hot molten core, magma core, on the inside of the planet. Here, this is Earth, but same on Venus. And you'll have hot spots. So they're like convection currents. They just really go up and out. And these, in part, drive the tectonic activity. So, I don't know what's going on with Venus. But anyway, if you just have a hot spot that doesn't move around, you'll have, continuous flow of hot liquidy material going up. And if you get a weak spot in the crust, then boom, it comes out, and lava will run out, and over time build up a higher and higher volcano. So those are known as shield volcanoes, and that's what we see on Venus, not other types of volcanoes at plate boundaries, because there doesn't seem to be any plates. What else is going on the surface? Well, we don't see as much crater activity as we would expect, and it's pretty obvious in one sense why this is true. Venus's atmosphere is so dense that just to get down there to the surface is an ordeal. It's pretty hard on Earth to get through our atmosphere without burning up. You really need to either be really big so that by the time you reach the surface, not everything has burned up, or you need some advanced alien technology like heat shields to protect you from burning up. On Venus, since the atmosphere is so much denser and actually higher, as we're going to see, it's higher up goes farther out into space than Earth's atmosphere, even though Venus is slightly smaller. Um, Smaller, medium-sized meteorites will burn up before they hit the ground, so we don't really see craters smaller than 2 or 3 kilometers across. Those are pretty big craters. On Earth, small enough meteorites to make a crater 30 feet across, or about 10 meters across, can make it to the ground. So that tells you the difference between the densities of the atmosphere. 10 meters versus 2 to 3,000 meters. Oh. So, but we can still use crater number estimating. Remember in Mars we talked about tree rings versus crater density and how it's a similar. You can use it in a similar way to estimate the age of something. Estimating the age of the surface of Venus using craters, uh, it appears as though it's a very young surface on Venus. Young meaning that the the older surfaces would have been completely covered over by something new like lava. And yeah, so it's thought that volcanic activity would be frequently covering up older areas of ground with lots of fresh lava. So possibly the surface in some places is as young as 100 million years old. So, and this is awesome. When I first saw the picture of Venus, which by the way, this is I just found these literally a couple days ago. I've never seen the edited versions of these, but this is a picture from the Soviet Venera probe, which landed on Venus, and it's a I think spherical picture, so that's why it looks all weird and distorted. But still, I looked at this picture. I think I first saw a black and white one, but then there was a colorized one. They used this right here to try to get real color, although it's pretty hard on Venus with because you gotta take into some other effects like scattering and stuff. But anyway, when I first saw this, I was like, oh my god, that's so cool. That's what Venus looks like through all those clouds and crap. And I think this is another picture. So they sent in the 70s. The Soviets sent some probes to Venus's surface, and they took some pictures that look like this. These are the only pictures we have so far. Not many. If you do a Google search, they all look very similar to this, and there's not a lot of them. It didn't. The probes didn't last very long on the surface. I think about an hour or so each before all the instruments got destroyed. Because it's really hot here. It doesn't look super hot, but it's 800, 900 degrees here or so. The pressure is super high. It's like literally being deep in the ocean. So it's not ideal ideal conditions to pitch a tent and camp out here. But then I just saw this the other day. Like this guy Don Mitchell took these pictures and then used Photoshop to make to take it from the spherical view and kind of squeeze it together and make it more like what you'd see with a regular camera with your eyeballs. And this is cool because it really brings the horizon in to perspective. And I was reading up on it. Doing this method to like bring it together, it's more accurate on the edges, I guess. And as you get closer to the center line here and the center line here, it becomes less accurate. I'm not sure I understand exactly the processing involved, the Photoshop processing involved. But then this other guy, I couldn't find his name. This is the website I found it from, and in the comments section, his name was Thomas. But anyway, he tried to use like these colorized pictures to color Don Mitchell's pictures, and it was interesting reading the comments here. I might check this out if I were you, if you're interested. He was getting suggestions from other people on how to tweak the colors to make it more realistic. But again, this is like false color, so take this with a grain of salt. If you were really on Venus, I'm sure the color would look a little bit different. I don't know how much different, but still cool nonetheless to see a kind of normal picture that's pretty close to what the colors of Venus would look like. And it's desolate and it's barren and it's really hot, but it's still beautiful. This is the second planet. This is our second planet from the sun. So cool, so cool. So what did the Venera probes have to go through in terms of the thick atmosphere and to reach the surface down here? They had to go through all this. If you take a look, here is Earth's, and I squeezed it down so that it was to scale. Although I guess it looks like I screwed up. 100 is here. I wanted 100 to be the same. So what if I do that? Yeah, that looks like the hundreds line up. Right about there. So this is Earth's atmosphere. This is from basically top to bottom. Down here is the ground, and then as you go, here's cloud level, and then as you go higher, you eventually reach space up here. This is Venus's. Look how much higher. It's about twice as thick. I mean, I don't know if these pictures actually represent, the cutoff where you consider it to be space versus atmosphere, but at least in terms of appreciable atmosphere, roughly maybe twice as deep, like an ocean of sulfuric acid and mostly carbon dioxide and nitrogen, but we'll talk about that. Anyway, so Venus's atmosphere is very different from Earth's. It's about 90 times more massive and goes much higher into space than Earth's. Earth's goes maybe 100 kilometers or so, maybe a little more before you reach probably what might be considered space. And um, so let's talk about these graphs here. On the side is altitude, so this is height. Planes, fly around in this area. And over here is pressure, atmospheric pressure. You know that if you go up high on a mountain, the pressure is lower, and so you might need oxygen mask to breathe. If you get too high, you need like a suit, space suit, because the pressure is too low. And so at the surface of Earth, it's 1 atmosphere, 1 bar. And down here we get temperature. So you can see the temperature at the ground on Earth is roughly about, on average, 280 Kelvin. If you're not familiar with the Kelvin scale, just do some Google converting. Just type in like 200 Kelvin to Fahrenheit or Celsius, and you'll see roughly what temperature that is. Then as you go higher up, the air pressure decreases, and the temperature doesn't always decrease. It actually decreases to about the cloud level, then it increases again, then it decreases. In fact, where it changes from increasing to decreasing is where we define, is whether people or atmospheric scientists define the boundaries. And so the troposphere, where the clouds kind of end, is at about a height of 40, 50, 40, 30, 20, like 12-ish, 12 to 15 kilometers. Look at Venus's troposphere. 100 kilometers. Whoa! Look how high the clouds are. 50 kilometers. Like the main sulfuric clouds above the sulfuric acid haze. Look at the temperature. 750 Kelvin. Convert that to Fahrenheit and you'll be amazed. Well, let's do that. I'm going to pause it. Bring it. You ready? 750 Kelvin is close to 900 Fahrenheit. 900. I cook chickens at 450. Like half as much. Really hot. But look at this. 280 Kelvin is the ground temperature on average. Where's 280 Kelvin here? Right about here in Venus. So to reach that temperature, you'd have to be up in the clouds. So really, if you're like 50-ish, 50, 60 kilometers up, temperatures aren't that bad on Venus. But you'd have to have some sort of aircraft that hovers around here, or some sort of thing that you live in. But as soon as you get below this cloudy area, basically almost the top of the troposphere, that's when the temperatures start really getting blistery. So yeah, the troposphere is about 100 kilometers versus 10 kilometers. Temperature is really hot, and there isn't a lot of variation here. This is the only picture I could find of this plot, and I don't know if Venus also has like some other stuff going on here, like Earth fluctuates back and forth. Maybe Venus goes even higher, but they just didn't put it in this picture. That I don't know. But also take a look at the atmospheric pressure. Oh, and I'm going to stop the video after we talk about that. 1 atmospheric pressure is what you feel just sitting watching this video. That is, again, also up in the cloud level in Venus. Once you go below, you reach 90 atmospheres. It's 90 times the pressure. And in comparison, sorry for the abrupt pause. I was trying to find comparison here. So I'm going to go over just a tiny bit. Oops, where'd you go? So this is interesting. So Venus' surface is at 90 bar, and in the ocean, if every 33 feet you go down, that's 1 bar. Or every 10 meters you go down, that's 1 bar. So if you go down to 90 bars, that's 33 times 90. It's about 3,000 feet, which is less than a mile. That's how much divided by 5,280. That's a little over half a mile deep. So if you go down a half a mile in the ocean, which is, if you've ever swum in a swimming pool, you can imagine a half mile. That's really high pressure. Although this is cool. Whales, it looks like, can their lungs can collapse, and it looks like they can reach 7,000 feet deep. That's pretty deep. So this is not at the bottom of the ocean pressure. It's not that bad. It is gas, by the way. This is not liquid. Liquids can exert much more pressure because they're more dense. But still, 90 bars of pressure is a lot. That's another reason why probes have a hard time landing down, surviving down here, the high temperatures and the high pressures. Alright, that's a good place to stop. And the next slide we will talk about what the atmosphere is made up of. Alright, see you in the next video.